you divide by omega c. So by that you can easily, first you design a low pass filter, then you can easily transform high pass, band stop. The Bible for these filters is Mathai Young Jones. That is the only book, the heritage book for the filters. Whatever you want to know about filters, you can get from that. And before going to all these high-end books, one should start with Rider, transmission lines, fields line by Rider. First part is a lumped theory. Second part is a distributed theory. And if you can find out the equivalent of the distributed theory in the form of a lumped theory, you can understand the theory and do the design. And this is the summary of bandpass filter. Before that, you should know what is a K inverter and a J inverter. K inverter and J inverter are no other than a quarter wave transmission line only, because you know very well the other name for a quarter wave transmission line is a inverter. If it's an impedance one, it is a K inverter. If it is an admittance one, it is a J inverter. In the ZS equation, if you put L is equal to lambda G by 4, then you will get Z0 square is equal to ZS into ZR. If you put L is equal to lambda by 2, ZS will be equal to ZR. If you put L is equal to lambda G by 8, you will get modulus of ZG is equal to modulus of Z. So because of this only, the other name for lambda G by 4 is an inverter. That is the reason in a Smith chart, you plot a point and go to the opposite. So opposite going means it's traveling by lambda G by 4, it is getting inverted. So it is used for two things. One is for matching Z0 square is equal to Z into ZR, or you can take one to the other side and make as an inverter. And this is a take-home message. K inverter or J inverter, pre and post connected by an impedance of Z0 with a length of lambda G by 4 can easily be represented in the form of a coupled transmission line. And in a low frequency, if you say two networks are equivalent, the meaning is both have got same impedance, short circuit impedance and open circuit impedance. Whereas in the microwaves, if you want to say two networks are equivalent, the meaning is the ABCD of one should be equivalent to the ABCD of second. If you take this principle, you can easily get the ABCD of anything. If you want to get ABCD of K inverter, first of all, write the ABCD parameter, then replace theta as 90, then you will get this. Then you can make use of the Richards transformation. J tan beta is equal to S. If you do that, then you can express everything in terms of ABCD. Then ABCD has got another two names, transmission line parameters as well as chain parameters. And it is used for transmission lines, and also if there are more number of elements, for each one you write the ABCD parameter and then make a combination, and that's why it's called chain parameters. So this slide is the summary for the bandpass filter, and also for the open circuit, short circuit, ZOC and ZSC, and ABCD parameter that you can easily derive also. Expressing V1, V2 in terms of I1 and expressing V1, I1 in terms of V2 and minus I2. And just like that, I told LNC are the two things throughout the world. There are only two types of connections, inductor, series connection and parallel connection. So that ABCD is 1Z101, and for admittance it is 10Y1. And lossless transmission line also you should know. That also you can get from the ZS, cos beta L, J Z0 sin beta L, J sin beta L by Z0. And also here only you can use the ABCD parameter properties, AD minus BC1, real quantities, imaginary quantities, and the transformer ABCD parameter is known. And finally, this S parameter, one should know in microwaves, H parameter are seldom used because it's a short circuit, open circuit, whereas that are not stable and there are no measurements possible also. Then that's why you should go for scattering parameters and you should know the properties of that. So these are the summary why we have to go for S parameters. All these things you can get from that manual. application note 154. And these are the definitions. And S11, S22, initially what students study is reflection coefficients. Reflection coefficient in the input is S11, reflection coefficient in the output is S22, and the transmission coefficient, gain or loss, is expressed in S12 and S21. And by flow diagram, energy flow diagram, also one can get easily the gains. And this diagram will tell you how to get all the 9 power gains of an amplifier. If you know the conditions from each one, you can go to the other one. And this is the summary of that. And one should be thorough with the network theory. Then only you can find out the equivalent or the analogy of a transmission line to the network theory. Mainly the image impedance, iterative impedance, those come in the case of a asymmetrical network. Whereas for a symmetrical network, image and iterative will be same. And that's what we call it as the characteristic impedance, which is equal to root of ZOC and ZSC. And we know what is OC and SC impedance. From that only you get Z0 is equal to root of Z0. If you substitute, you will get again Z0. Then input impedance is AZL plus B by CZL plus D. Now you make ZR is equal to 0, you will get ZSC. You make ZR is equal to infinite, then you will get ZOC. Then take the square root, then that is the characteristic impedance. Once you get effective ABCD parameter, you can make use of this relationship and then get what is the equivalent scattering parameter. Here also you can simplify, because you know very well for certain conditions AD minus BC is equal to 1, A and D are real, B and C are imaginary. Then you should know when A and D are equal. If you know all those 3 conditions of ABCD parameter, you can make the computation easier. And for any ideal transmission line, S11, S22 are 0. That's why ideal transmission line, the S parameters, S matrix is given like this. So this slide gives the summary of all the S parameter and interconnection. And this is a small example by which input matching network, output matching network, it is only L section. And again, one should revise the matching networks found in the network theory. The ideal book is Everett and Anner, where L matching and T matching. Normally we don't use the T matching here, only L matching. If one element is L, the other is C. So you should know what should be the length and what should be the width. To know the length, you find out the ZSC, ZOC equation. To know the width, you find out what is the impedance. From that, you can find out the impedance, that you can make use of the Smith chart and then find out. So this is an example where you can see the layout design of inductor and a capacitor in the case of input matching and output matching. In the case of oscillator, there is no input matching, only the output matching. It is L and C. These are the, initially I told, the backbone of MIC or the planar transmission lines. The first one, 51, because during the 1951, small devices came, trapet, impact, pin diode, all those things. Then how to connect that with the waveguide? Then there was a need for a small integrated circuits, and that's why 51 strip line came, microstrip, next one slot line. This is only 50% of the representation. Immediately after drawing the cross section, you should draw the field lines. The field lines, you should go from the signal line to the ground, just like what you do for an electrical generator, from positive to negative. After drawing the E lines, perpendicular lines you draw for H. And if you want to know the characteristics of each transmission line, you need not mug up its properties. If you know, you should classify to which mode each belongs to. Strip line is the best example for a pure TEM mode. For a pure TEM mode, there is no epsilon effective. It is only epsilon R. Whatever is the characteristics of TEM, that is the characteristic of strip line. And microstrip is the best example for quasi-TEM mode. Quasi-TM mode, it has got almost same behavior as a TEM. Only thing is EZ, HZ are not zero, unlike strip line. Then slot line, it is not having a ground plane, only the top plane, and it is the best example for non-TEM mode. And coplanar waveguide, again it is not having the ground plane. It has got left side, right side are ground, and center is the signal line. And among these planar transmission line, two things one should know. What is the impedance, low impedance, high impedance, and also the frequency of operation. If it's a millimeter, the slot line and coplanar waveguide are the better choice. Then there are many more planar transmission lines. Then lower microstrip, you can go for a strip line, microstrip, and other things. And among strip line and microstrip, what you do is replace all epsilon effective by epsilon r, then you will get the strip line equation. And strip line, if you want to connect some components, you have to drill a hole, and that is slightly difficult compared to the microstrip. So that is how you can find out what are its merits and demerits, and then accordingly you can choose. In any case, two things are important. What is the high impedance, low impedance method, and also what are the frequencies, and also tan delta. Tan delta will tell you about the substrate. And the best book, one and the only book for strip line is Harley and Ho. The Bible for microstrip is T.C. Edwards. The Bible for slot line and other things is K.C. Gupta, Amarjit Singh Gupta, Garg. So these three persons have done, and there are classic papers by Kahan. Similarly, CPW, there are only two books. One is R.N. Simon, is an Indian, and another book is Wolf. And R.N. Simon book is followed throughout. Wolf also is referred. And the complement of coplanar waveguide is the coplanar strip. And take a coplanar waveguide, put inside a waveguide, and that is termed as a fin line. The one and the only book for fin line is again written by Indian, followed throughout the world, is Professor Bharati Bhatt. So that way, for each of the planar transmission lines, you refer. But initially, one should not, you can do the reference at the end, but you should derive everything, and then you can refer at the end period. And the planar transmission lines are very, very important, and you should know the modes, which each one will separate. Each one will support. These are the few transmission lines, and there are variants. You can invert it, you can elongate it, you can have a V groove, many. There are 36 variants of the planar transmission lines, and you can remove the substrates even. If you remove the substrates with a proper angle, and that is the cross section of the micro electromechanical system that is used if in the biomedical side is the biomems. And what you should note from this is what is the low impedance and high impedance. If you see microstrip and strip line, low impedance is 20, high impedance is 100. Whereas if you go for fin line, the high impedance is 500. So you don't remember in terms of the numbers, simply think about low impedance and high impedance. And from the Wheeler's theory, we know that high impedance have got low width and low impedance have a broad width. And these are the various period during which the transmission lines have been found. But in microwaves, there is no history at all. What was found during Maxwell's time will be used many more years. Nothing will become obsolete. TWT, Klystron, everything is used for different purpose, and none of the inventions will become obsolete one. That's why I keep referring microwaves as Gitanjali. It is ever fresh. And these are the materials. substrate materials. Generally, the students, they go for FR4 for different reasons. But RT Duride is very costly. You should know what is the epsilon R. And alumina has got a higher value. Whereas once you go for gallium arsenide has got some 15.6, likewise silicon. Many kinds of substrates are there for different purpose, and each has got the tan delta is very important, and that only will tell you how good it is. And generally RT Duride, alumina and silica, this FR4 are the one used by for all the experiments what we do in our labs. And we have got materials. And this is a small comparison. The epsilon R of, this will be useful for biological effect. And the epsilon of R of a bone is 50. The epsilon R of air is 1, whereas the epsilon R of a brain is 50. That's why there's a theory that using cell phone for a longer time is not advisable. Each part has got different epsilon R, and that comes as a big ocean called biological effect of microwaves. And we got a stalwart, again an Indian by name Gandhi, O.P. Gandhi. He has done a lot of work on biological effect of microwaves. Dr. Girish Kumar has done a lot of work. And these are the various planar transmission lines. And you can do many ways. You just take a strip line or microstrip, suspend it. If you suspend it, you will get the benefit of air as well as the substrate. You can invert it. You can elongate it. You can so that's how variants are there. The classical planar transmission lines are 5 or 6. But with that, you can form other planar transmission lines. Now, you take a simple patch antenna. If you take a patch antenna, normally you can see people say use already available expressions, but one can easily get that expressions. If you take this patch antenna, it has got one length and the width. The length is almost in terms of it is lambda g by 2. Resonator, you just subtract the effective length, the correction factor delta L left side and right side. That is how the length and width values are little different. It has got major 3 components. The patch, you can find out what is its impedance. Then the 50 ohms line. And the 50 ohms line, if it has to be connected to the patch impedance, you should make use of the quarter wave transmission line in a simple way. That's how the central line has come. You should find out what is the root of ZS, ZR, find out the impedance. That impedance is more. That is why the central line is width is lesser. The left side is 50 ohms line and the other one is patch. So every dimension we use, you should know how to get, or you should derive it. I found some people simply take on paper and take all the dimensions, change it little bit up or little bit down and find out some new theory. But otherwise, what one should do is go from the lambda by 4, magical lambda, 0 to lambda. It is not only lambda by 4, lambda by 8, lambda by 16. Many lambdas, 0.04 lambda, 0.05 lambda. If you go through the theory of FSS, metamaterial, you can see such lambdas. Why such lambdas? Then you can know the reason. So that's how you just go from the fundamental theory and then start deriving. And this is a small example of how to get the values, the layout. The layout is very important. The next one. So if just like the conventional antenna, if one antenna's gain and directivity are not sufficient, then you can go for arrays. That's how you have got this, the first one, the arrays, patches of array. And here when you want to do the connection, you should go for the dividers. Dividers also, every divider, you make use of the formula Z0 squared is equal to ZS into ZR. That's how you should find out what is the length and the width. And finally, you should take care of the discontinuity also. End discontinuity, gap discontinuity, Likewise, that's why you would have seen the end part metering. So that way, every component you take, you start from the basic design, and one should not go directly to the software and go for the easier method. These are all the antennas. Now you can see Yagi-Uda array even. If you take the Yagi-Uda array, this is the MIC version. Once you get the layout, you can get it in microstrip, strip line. And one thing easy in the microwave, there are two things theory made easy for the design. One is the half mode theory, even mode theory, and odd mode theory. Because of the symmetry, it will be sufficient if you do the analysis only half mode way or in the even mode way. Similarly, we talk only in terms of lambda g. Lambda g is equal to lambda naught by root of epsilon effective. So that if you know in terms of lambda g, it will not be different for different transmission lines. If it is a coplanar waveguide, use that epsilon effective. If it is a strip line, use that epsilon effective, mainly epsilon r. So just like in a Smith chart, if you know everything in terms of lambda g, the design concept is same for all the planar transmission line. Only thing is the cross section will be different. So if you take, and this is an ideal example where one can see the effect of lambda in the different lambdas. What is the distance altered different lambda? So everything you can tell in terms of lambda and go for the design, whether it is RA50. So these are the few components. Most of the components what I am showing is designed for S-band. If you go to the microwave 101, you can know why this name. If you know the reason for the name, you will never forget why S is called S, why Q, Ka, K. If you know the reason for all these things, best material that can be referred is a microwave 101. For example, klystron, just like gun diode, klystron is not the name of the person. Klystron name itself will tell you it is the velocity modulation, klysine, breaking of the waves on the seashore. Likewise, you get the name, why it is, why, then you will not forget. Similarly, you just practice yourself designing in terms of lambdas, then any type of component can easily be got. No trial and error method. Then only you can go for optimization or whatever it is. So this is what I have been telling about even mode analysis and odd mode analysis. Whenever you have the mirror symmetry, just like in the SIW, you've got half-wave mode, quarter-wave mode. These are all happening because of the symmetrical nature. You just cut it. That's what we have got: electric wall, magnetic wall, corresponding to short circuit, open circuit. Computer will understand, man will understand the visibility. Then computer will understand the circuit theory. And you should make it in the even wall and magnetic wall, then go for the analysis. So the problem will be reduced to 50% by this method. So that's why everywhere you need, if it is a short circuit, ZSC. ZSC means it is JZ not tan beta L. In that way only you should get all the values. Similarly, OC means Z not by J tan beta L. Then go for the, now we have got the three section. One is two shunt values and one series value. For each shunt and series, you find out ABCD parameter, then multiply it. Then get effective ABCD parameter, get everything. So you should be able to find out the impedance of each shunt arm, series arm. Once you find out the impedance, you can easily get what is the width value and what is the length value. So everything you should design from the scratch. And these are all the components. Whatever you see, the waveguide components, every waveguide component you can, if you take one directional coupler, waveguide directional coupler, that will be weighing some 1 kilogram, that you cannot place it. Isn't the main aim of microwave is miniaturization, isn't it? We are very good, Indian top in the space applications. In all satellites, the volume and weight are very, very important. That is possible only when you go for the integrated circuits. And micro electromechanical system, it is not centimeter, it is micrometer, then nanometer. So miniaturization is the mantra in all the design of bio MEMS, everywhere. That is why it becomes very, very small. Only thing is at the cost of power. And there's a method of getting the power also, power compensation also is possible. So all these components you can easily convert into the MIC components, MIC methods. And this is one such method. So this is people would have known about the super heterodyne receiver. That is in the form of a mixer. If you take a mixer, you got almost all the components. You got a rat race, you have a matching device, you got a low pass filter. So many components are there, and each you should design separately, then integrate it. In fact, in mixer or a double balanced mixer, even planar transmission lines will be coming in different planar transmission line, fin line, microstrip, CPW. Whenever you want to change one transmission line to the another transmission line, you can make use of the antipodal fin line. So antipodal line fin line is very popular, isn't it, for changing one transmission line to the other transmission line. If you go to the SIW, and another thing I want to say, there are some heritage books. Each topic has got one book. There is a book by tappering, isn't it? If you take a SIW, there will be so many tapperings: cosine tapper, sine tapper, different kinds of tapper, exponential tapper. That's a very big theory. That's a book on tappering alone. So that way, the classic papers and books will be of much use. So whatever I have shown this, that has been realized in the microstrip form, in a strip line form. You can, this is the layout. You can just transform in the form of a microstrip or strip line, or in any other planar transmission line according to the principles. Now you can see low pass filter is there, local oscillator is there, RF port is there, diode port is there, matching is there, output port, everything is there. You can minimize it. So you can make it in the millimeter size, micro size, or whatever it is. So only I just made a small attempt of not using the commercial software. You take the principle, make use of the MATLAB, you do the design. Draw the, in this, my scholar, Dr. Samson has helped me a lot. And you make use of the MATLAB, do the design from the scratch. So all the components of whatever I mentioned, including the theory, that has come recently by the CRC publication in this book. It is a micro MIC components designed through MATLAB. All the components with the essential network theory, and that by the MATLAB code. And I feel proud to show this slide. And she's you would have seen her name in Abdul Kalam, Dr. Abdul Kalam's Wings of the Fire, Professor Bharati Bhatt. And she is a stalwart. In her book, she has written the first book. What I would like participants to refer is Strip Line Like Transmission Lines, written by Professor Bharati Bhatt. And Finline book, Finline she has done. And what is the uniqueness of the books written by all Artec publications, written by Professor Bharati Bhatt, is she has done enormous analysis, enormous investigation herself in the network analyzer. Whatever is working, that has come as in the form of book. Whatever is in the book, that has come in the form of book. Most of the, maybe Professor Mahadevan will tomorrow, how her theory is helping in the designing many of the components. ISRO people use it, DRDO people use it. So it is not just like for exam point of view. So in any case, we owe a lot to her, Professor Bharati Bhatt. Many books and phase shifters. Phase shifters, 2 books are there, and that has been used in radar. Direct design. It is not just like writing exam and exam questions. Phase shifters. Many real good books have been written by Professor Bharati Bhatt. I feel proud to show her, and she has written the foreword for the book, whatever I have shown. And so this is one. If I have been able to see farther than others, it was because I stood on the shoulders of giants. This holds good for many of the theory. And this is the one about the, I think I will take another 20 minutes. And this is the Richards transformation about take a small transmission line, open it, it will behave as a capacitor. Take a small means what is small? Anything less than lambda g by 4 is small, because whatever you do after lambda g by 4, theory will be in the opposite. Plus j will become minus j. You take lesser than that. Among lesser than lambda g by 4, if you take lambda g by 8, it serves some other important purpose. Tan of that will become 1. In any case, lambda by 8 is another popular length of transmission line. You make it as lambda g, then it will hold good for any of the transmission line. So this is how we get the stub method of getting L and C. I already shown the high impedance, low impedance are other method of getting L and C. And this is the one to convert using, this is called Kuroda transformation. Each transmission line, some are good for series alone, some are good for parallel, some are good for series and parallel. So we have this theory, Kuroda transformation, which converts series into parallel, parallel into series. Using this, once you do the computation analysis, make use of this theory and easily convert all series into parallel or all parallel into series. And to make this Kuroda transformation, you should derive it. How to derive it? Left side, if you take a admittance, you write its S parameter, ABCD parameter. You take a unit element, and the unit element also is a transmission line of the value of Z0 is equal to 1 and length as lambda g by 8, 4. And that ABCD parameter you take down, find out the combination, and that you equate it. I already told, in high frequency, if you want to say two networks are equivalent, the meaning is ABCD of one should be equal to the ABCD of second. So that way, you can easily derive how to get the corresponding elements in the Kuroda transformation. So it's only two ABCD, left side, right. Only thing you express everything only in terms of ABCD method, then you can get inductor will become capacitor, capacitor will become inductor, short will become series, series will become short. With this theory, you can get all four. Among these four, third and fourth is transformer. With using transformer, that we don't use much. Among first and two, second is nothing other than the first. It is in the reversal form. So what I want to say is, nothing should be mugged up in the microwaves, and what need not be feared about the Maxwell's equations also. You can simply using the simple theory and keep deriving. So this Kuroda transformation, so this will be very much useful in the, you can see in the application of the filter, how the series will become shunt, shunt will become series, just like tables. You can take down and then make use of it, get the values in impedance form. And this is the small example of using the Kuroda transformation. First, in the filter form, you get what is the order. Only from the order specifications and the insertion laws, you can easily get the order. This is a simple three-section filter. You get the G values, either in the Chebyshev or Butterworth or Bessel function, whatever may be the function, get the values of G values, draw the lumped one, then get the equivalent distributed one, the inductor shorted short transmission line, capacitor open short transmission line. So that way you represent in the distributed way. Then if you want to represent the series only into parallel or parallel only into series, again you just add unit element. By adding unit element, the property will not get changed. So that way you can have the component fully series or fully parallel. Fully series of not much use, but fully parallel will be of very much use if you want to realize in some transmission line. So that's way here you can make use of the Kuroda transformation and then go stage by stage and finally get up to this. Now this is what finally you get. After the pre-final layout, multiply by the characteristic impedance. everyone know why we take Z naught is equal to 50 ohms. For any theory, if you want to know why, you refer micro 101. If you also find out some new things, my own student got 3D Smith chart. So he sent it to the editor, and now everyone can see. Likewise, if you come out with some new ideas, communicate to the micro 101, they will add it, just like different versions. So now you can see 3 ohms, and the highest ohms has got the least bit, and least 50 ohms has got the highest bit. And once you get the impedance, make use of the Wheeler's curve and then get the bit. And here there are two, I already told there are only 2 methods of getting L and C. One is high impedance, low impedance method, or stepped impedance method. The other one is stub method. In the stub method, every part is lambda g by 8. Whereas in the other method, lambda will get changed. Whereas in the other method, width will be same. Here it will be different. Here every length is lambda g by 8, and the width depends upon the impedance. So this is the best example I can give for making use of the corona transformation. And this again many times you have seen: shorter transmission line, open transmission line. Then in the theory, if you make use of all these things, you can easily get what is ZOE and ZOO. This only will tell you how to get ZOO and ZOE for the coupled transmission line. Especially band-pass filter, you need coupled transmission line. It is not only band-pass filter. Whenever you need a coupled transmission line, you should know how to get the values of ZOE and ZOO. And ZOE, ZOO also, for even mode, odd mode, you can separate. Then you have got 4 impedances. Whatever may be the impedances, ultimately you can make use of the nomogram and then get what is the value of the width. Because out of the 3 dimensions, H is the manufacturer's concern, width and the length only we need. Length we get in terms of lambda g, width you get in terms of the impedance, either OC, ZSC or OE, OO. By this you can get all the values. And this is the small example of this layout. You can see the center one, and generally in microwaves, see here you can see so many L and C. That's why I told, if a person is thorough in the design of filter, he will know everything about L and C. So when you can design then 5 section, 7 section, isn't it? In the case of microwaves, we should go mainly in terms of in odd values only. Even if by specifications, if you get even, you should go for the next odd. Then only symmetrical main design and characteristic impedance can be easily matched. So you can get 7, 9. When you can do 7 section LNC, designing one LNC will not be difficult. So that is why I told all the theory needed for microwave theory will come once you design a filter. And if you take a patch antenna, it is only LC. Equivalent circuits are very, very important. If you take a magnetron, each cavity is LC. So 8 LC will be there. So it's only LNC that is derived by this. Whether it is a Chebyshev butter, whatever it is, what we want for the design is what is G values. Then you can go for the frequency scaling, impedance scaling, and go for the real value. And this is the next one. In the next few slides, I'll just show, at least I should do justice for the topic of the 6-day seminar. What are the trends? There are many trends, each one will tell different thing. From my part, I will tell what are the hot field. I will tell slowly by that. The first one, Richard Feynman. Richard Feynman, he told, he got Nobel Prize also, there's plenty of room at the bottom. That made many come out with so many theory, and that is micro electromechanical system that used in biomedical side is in the biomems. In India, there are some 3 places where a lot of work is going on: SCL Chandigarh, then BEL, and a few more places where labs are going on. And being in Kerala, NPOL is doing a lot of work on the using the software, co-inventor software. And so MEMS and Richard Feynman is the reason for the MEMS. And this is the small cross section. If you see left side, plane view, it is nothing other than what we say patch antenna, but it is not in centimeter, it is in micrometer. But if you see the cross section, it is at 54.7 degree, you make a cut. Why 54.7? You can see. And here silicon is used. We don't use silicon in the MIC circuit. We go for silicon is the popular one. Again, you should know why. And using silicon, and you cannot remove fully. You should remove only partially. If you remove partially, losses will be reduced. Every MEMS device you take, the cross section will be like this. So again, why I am telling this MEMS here is many of the cross section of the MEMS will be a coplanar waveguide. So again, the continuation of the micro integrated circuit planar transmission line, that continues. Only the size will be different. Centimeter will become micro MEMS. So this is again a very good field. RF MEMS, a reconfigurable one, especially bio MEMS. The engineering doctors and medical engineers are very, very less. If they join together, wonders can be done. And not many papers from India on this plane, and that many can do work on biomems. Sri Chitra Tirunal Biomedical Center is the center of advanced study for biomedical engineering in India. You can see wonders. There's a separate division where material. In Trivandrum, there's a Sebastian. MT Sebastian's book is a very good book for material characterization. So one can see that, and this is one part I can say people can work on this. And RF MEMS book, Cochin University professor has written, KG Vinay, that book is a very good book and for RF MEMS. And this is the MEMS lab. Like astronomer, one should go inside and do. This is again in Kerala state only, but in a bigger version, SCL Chandigarh one can see. And these are the software available for microwaves. And what I strongly advise is this software should be used at the final design point or at the final verification. But initially, as far as the researchers are concerned, you should know the techniques, numerical techniques, and then do your own analysis. You should write your own coding. Then many things, papers will not get rejected at all. You can write your own theory. Good number of research can come. And each software is based on some theory. One is on FEM, one is on another is on FDTD. Tomorrow there's a session by Dr. Mohan on FDTD. Then method of moments, IE3D is method of moments. Method of line, there is no software has come so far. Then integration technique. So different techniques are there. Using that technique, softwares have come. What I strongly advise is, one can even go for the analytical way also, not by experiment or anything, purely by analytical method, full wave analysis. There are two types of analysis called full wave analysis and quasi-static analysis. If this from the dispersion, if it can be tolerated, you go for quasi-static. If it cannot be tolerated, then you should go for full wave analysis. For the design, full wave analysis is definitely better than quasi-static. But for easy experimentation purpose and all easiness, you can go for quasi-static. There are merits and demerits. So that way, you would be Hello, can you see?
Yes, sir.
Hello.
Yes, sir, we can see.
Okay, okay. The lower above 12 gigahertz, you can see that W and frequencies do not have a linear relationship. That is what we say dispersion. Above 12 or nearby frequencies, microstrip, you should not go for quasi-static analysis. Likewise, for each planar transmission lines, you should see what is the dispersion analysis, then accordingly you should decide. So that is what is meant by static analysis and full wave analysis. In full wave analysis, only all those techniques are there. And this is a few examples of the software available. And recently, our own Kharagpur person has come out with a Make in India own software by Swapnil. Purely Girish Kumar, our own professor John and come out with is a monk. Is a person, and the monk theory, you may be knowing FSS. This is a very, very, very hot field, frequency selective surface. And this, even though I say it is the hottest field, this started from Marconi. Marconi, it is a patent. One of his work, it was a patent. That only afterwards Dr. Monk took and then developed it. And it is again a filter only. FSS is a spatial filter. And some last month, India got the Rafale flight, and it has got more FSS characteristics in terms of in the antenna, radar cross section. FSS is the hottest field. We can number the people who are expert in India or in the whole world. So the starting person is Monk. This FSS Monk has developed a lot of theory, and this is a small FSS structure, again developed by initially developing on simple unit cell and multiplying it in different unit cell, and again developed by my scholar. And this work has got award also, 5 lakhs award by DRDO. It is not the award, the usage of that. The usage of that is the enemies cannot see our flight, but we can see others. So the radar cross section can be minimized and many more advantages. So that is the FSS. FSS is not only for defense; it is for biomedical purpose. Many of the CT, MRI machines safeguard the patients, but which one will safeguard CT, MRI? FSS can safeguard the CT and MRI. So people can take the Monk book, get many papers. Those who are going to start the work, definitely FSS will bring them to the great height. FSS is very, very hottest field. Very, very few people are then in India doing that. And this everyone know. Veselago, he told negative mu and negative epsilon possible sometime before 1968, and that has become reality now. And that is what we say metamaterials. Metamaterials, one should be thorough with even for all these things, one should be thorough with the transmission lines. And for metamaterials, make epsilon or mu or less than 0. That way, Maxwell's equations, you make epsilon or mu or less than 1, then that will become the metamaterial theory. And this is again a good field, metamaterial. And people go for fractal antenna. Fractal antenna also keep minimizing using the binomial theory or any of the mathematical theory, then go for the design. This also come from the nature. And this is the conventional antenna. Why I am showing that is, when there is space is a problem, weight is a problem, the conventional antenna is of no use. But this has got other advantages also. But when you go for the implantable antenna, then in general, there is nothing to beat conventional things. See, even now we face a lot of problems in the transmission. It is nothing equivalent to blackboard teaching. Similarly, this antenna is the best antenna where epsilon or air is used. Whereas If you want to have the implantable antenna, biomedical antenna, then you should go for the smaller version. This is the few design of that biomedical antenna, implantable antenna, flexible antenna, liquid antenna has got another research trend. And this is a few examples of meta material.